We're going to talk about solving by factoring today. So the benefits of factoring, number one, it's usually the easiest method to solve quadratics. And then another clear benefit is that if it were graphed, you have x-intercepts clearly visible when you factor the equation. When to use factoring? If the equation is factorable. That's usually when you want to factor an equation. I know that sounds pretty obvious, but if it's not factorable, then you have to go to one of two other methods. If it is factorable, that's usually the best way to go about it, unless the problem tells you specifically that you have to do something else, or there's another benefit to doing one of the other methods. So factoring is probably our go-to method anytime we have an equation that is factorable. So once again, just a couple reminders before we go into it. If we are factoring, we have to make the equation equal to 0. So in other words, get everything on one side. Then we usually want to look for the GCF, if there is one. In most problems on this worksheet, there isn't, but you always want to look for the GCF because that'll help you. And then after that, you want to usually use double parentheses. However, there are some other methods that might help, especially later on, factoring by grouping or using some of the special cases that we have. Difference of two squares, sum or difference of cubes. So that might be something that you want to look into. And then the final thing when we're solving that we didn't talk about in another factoring video that we may have had earlier, when we're solving, we want to use the zero product property. And what the zero product property is when you have two numbers that multiply together to equal 0, that means that either A equals 0, so the two numbers are A and B, either A equals 0 or B equals 0 must be true. So one of those two things has to be true in order for the zero product property to even make any sense. If you have two numbers multiplied together to equal 0, one of those numbers has to be 0. That's just a rule, basically. So now I'm going to quickly factor some things. These 6 problems won't go very long in factoring anyway. So if I have x squared here, I'm going to lock in x and x. 39 is either 39 times 1 or 13 times 3. There's really not much of a choice. And in this case, 13 and 3 are clearly going to help us out. So I can then set x plus 13 equal to 0 and x minus 3 equal to 0, because by the zero product property, either x plus 13 or x minus 3 must equal 0. So in this case, x equals negative 13 and x equals 3 are my two solutions. If we look at x squared plus 10x minus 39, we see that the x-intercepts are negative 13 and 3. Problem 2, 4x squared minus 49 equals 0. There is no GCF. This is the difference of two perfect squares. So I have 2x and 2x minus 7 and plus 7. Then I set both parts equal to 0. So 2x minus 7 equals 0, and 2x plus 7 equals 0, which means that x equals 7 halves, or x equals negative 7 halves, are my two solutions. If we look at 4x squared minus 49, we see that the x-intercepts are negative 3.5 and positive 3.5, which are the same thing as plus or minus 7 halves. Problem 3, I actually have to make sure that everything gets on one side if I'm going to factor this. So 5x squared plus 30x equals 0. This has a greatest common factor of 5x. So I'm going to factor that out. So I have 5x times x plus 6 equals 0. Notice that if I distributed this back in, I would get back what I started with. So that's important to note when I'm factoring out a greatest common factor, or any type of factoring. I mean, if I factored any of these problems, when I distributed everything back out, I should get what I started with when I'm done. So that's just something to keep in mind. Now I can set both parts equal to 0. I get x equals 0 and x equals negative 6 as my two solutions. When we look at 5x squared and negative 30x, if we look at this graphically and we find the intersection points of those two curves, we see that they occur at the x values of negative 6 and 0, which are the same values that we got when we moved everything to one side and then solved the equation. Problem 4, I want to add 5 to both sides, so I have 2x squared minus 21x plus 50 equals 0. So I'm going to try factoring this. I know I just basically gave a hint that this is not factorable by saying that, but I can lock in 2x and x because 2 is prime. And then 50 has 50 times 1, 25 times 2, 10 times 5 as options. I can't put any even numbers in the red spot because there was no greatest common factor originally. And if there's no GCF up here, then there's not going to be any GCF after I factor it either. So I can't put any of the even numbers in the spot where I have a red underline. So that means I'm pretty limited in my choices. This spot can either be occupied by the 1, the 5, or the 25 because those are odd. So if I had 1 and 50, that's clearly not going to get me to negative 21 in the middle. If I had 5 and 10, that's also not going to get me to negative 21 in the middle. And if I have 25 and 2, that actually is, that's very tempting. That can get me to 21. Notice that 25 and 4 does get me to 21, but I have to put minus signs for both parentheses because this is a minus and that's a plus. And so if I did this, I would end up with the positive 50, but negative 25x minus 4x actually is negative 29x, which is not negative 21x. So I actually do not have something that's factorable here. And since this is not factorable, that does not mean that I don't have any solutions. It just means I can't tell them from factoring. So we're going to have to look at that in a different situation. If we look at 2x squared minus 21x plus 45 as the parabola and negative 5 as a line, we see that we have a couple intersection points. They're not rational, so that means that we can't find this by factoring, but they do have intersections. Problem 5. I don't have a greatest common factor. but 3 is prime. So I'm going to look at 3x and x here. 12 has 1 times 12, 6 times 2, and 4 times 3 as possibilities. Anything that is a multiple of 3 cannot go in here, so that really limits what I can try and will actually help me out a little bit. So I can put a 2 and a 6 in there. I know that everything's going to be positive because of the plus signs there. If I distribute this out, I end up getting back what I started with. So x equals negative 2/3 and x equals negative 6 are my answers, which I can find um, after I set both parts equal to 0. If we look at the curve 3x squared plus 20x plus 12, the parabola, we see that it intersects the x-axis at negative 6 and negative 2/3, which is exactly what happened when we found the solutions. I don't know what just happened. Oh, here we are. So in problem 6, I'm going to add 6 to both sides. 5x squared minus x plus 5 equals 0. So since 5 is a prime number, I can lock in 5x and x. 5 is only 5 times 1. So I can't put the 5 there because there was no greatest common factor at the beginning. So there's not going to be one at the end. So I have to put 1 and 5 as my only choices. There's no way I can get to this negative 1 in the middle. So this is not factorable as well. And usually what happens when something is not factorable is that we end up with irrational solutions or complex imaginary solutions. When something is not factorable. So those are the two things that can happen there. If we look at 5x squared minus x minus 1, and then the line y equals negative 6, we see that there is no intersection of those two curves. That makes sense in the fact that it is not a factorable thing. So these solutions would be imaginary. If I added 6 over to both sides, and I see y equals 5x squared minus x plus 5, and I look at that curve also will not intersect the x-axis. And if you take a look at the comparison between the distance between the curve and the x-axis and the distance between this curve and the line y equals negative 6, you'll see that those distances are the same. So the imaginary solutions to this system of equations would be the same thing as the imaginary solutions to where this crosses the x-axis.